In physics, radiation is a process in which energetic particles or energetic waves travel through a vacuum or through matter-containing media that are not required for their propagation. Waves of the mass-filled medium itself, such as water waves or sound waves, are usually not considered to be forms of radiation in this sense. Radiation can be classified as either ionizing or non-ionizing according to whether it ionizes or does not ionize ordinary chemical matter. The word radiation is often colloquially used in reference to ionizing radiation, e.g. X-rays, gamma rays, but the term radiation may correctly also refer to non-ionizing radiation, e.g. radio waves, microwaves, heat, or visible light, as well. The particles or waves radiate, i.e., travel outward in all directions, from a source. This aspect leads to a system of measurements and physical units that are applicable to all types of radiation. Because radiation expands as it passes through space, and as its energy is conserved in vacuum, the power of all types of radiation follows an inverse square law in relation to the distance from its source. Both ionizing and non-ionizing radiation can be harmful to organisms and can result in changes to the natural environment. In general, however, ionizing radiation is far more harmful to living organisms per unit of energy deposited than non-ionizing radiation, since the ions that are produced, even at low radiation powers, have the potential to cause DNA damage. By contrast, most non-ionizing radiation is harmful to organisms only in proportion to the thermal energy deposited, and is conventionally considered harmless at low powers that do not produce a significant temperature rise. Ultraviolet radiation in some aspects occupies a middle ground, as it has some features of both ionizing and non-ionizing radiation. Although nearly all of the ultraviolet spectrum that penetrates the Earth's atmosphere is non-ionizing, this radiation does far more damage to many molecules in biological systems than can be accounted for by heating effects. An example is sunburn. These properties derive from ultraviolet's power to alter chemical bonds, even without having quite enough energy to ionize atoms. The question of harm to biological systems due to low-power ionizing and non-ionizing radiation is not settled. Controversy continues about possible non-heating effects of low-power non-ionizing radiation, such as non-heating microwave and radio wave exposure. Non-ionizing radiation is usually considered to have a safe lower limit, especially as thermal radiation is unavoidable and ubiquitous. By contrast, ionizing radiation is conventionally considered to have no completely safe lower limit. Although at some energy levels, new exposures do not add appreciably to background radiation. The evidence that small amounts of some types of ionizing radiation might confer net health benefit in some situations is called radiation hormesis. Radiation with sufficiently high energy can ionize atoms, that is to say it can knock electrons off of atoms and create ions. This occurs when an electron is stripped or knocked out from an electron shell of the atom, which leaves the atom with a net positive charge. Because living cells, and more importantly, the DNA in those cells can be damaged by this ionization, it can result in an increased chance of cancer. Thus ionizing radiation is somewhat artificially separated from particle radiation and electromagnetic radiation, simply due to its great potential for biological damage. While an individual cell is made of trillions of atoms, only a small fraction of those will be ionized at low radiation powers. The probability of ionizing radiation causing cancer is dependent upon the absorbed dose of the radiation, and is a function of the damaging tendency of the type of radiation, equivalent dose, and the sensitivity of the irradiated organism or tissues, effective dose. Roughly speaking, photons and particles with energies above about 10 electron volts F are ionizing. Alpha particles, beta particles, cosmic rays, gamma rays, and X-ray radiation all carry enough energy to ionize atoms. In addition, free neutrons are also ionizing since their interactions with matter are inevitably more energetic than this threshold. Ionizing radiation originates from radioactive materials, X-ray tubes, particle accelerators, and is naturally present in the environment. It is invisible and not directly detectable by human senses. As a result, instruments such as Geiger counters are usually required to detect its presence. In some cases, it may lead to secondary emission of visible light upon its interaction with matter, as in the case of Cherenkov radiation and radioluminescence. Ionizing radiation has many practical uses in medicine, research, and construction, but presents a health hazard if used improperly. Exposure to radiation causes damage to living tissue. High doses result in skin burns, radiation sickness, and death, while low but persistent doses result in cancer tumors and genetic damage. However, calculating exact risk and chance of cancer forming in cells caused by ionizing radiation is still wildly unknown, and currently estimates are loosely made off of population-based data from the atomic bombing in Japan, which shouldn't be generalized to populations in other countries. The International Commission on Radiological Protection states that the Commission is aware of uncertainties and lack of precision of the models and parameter values. Collective effective dose is not intended as a tool for epidemiological risk assessment, and it is inappropriate to use it in risk projections. And in particular, the calculation of the number of cancer deaths based on collective effective dose from trivial individual dose should be avoided. Electromagnetic radiation, EMR, is represented as self-propagating waves. EMR has electric and magnetic field components that oscillate in phase perpendicular to each other, and also to the direction of energy propagation. EMR is classified in two types according to the frequency range of the waves. These types include, in order of increasing frequency, radio waves, microwaves, terahertz radiation, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Of these, radio waves have the longest wavelengths, lowest energy, and gamma rays have the shortest and hence the highest energy. A small window of frequencies, called the visible spectrum or light, is sensed by the eyes of various organisms. Ionizing electromagnetic radiation is that for which the photons making up the radiation have energies larger than about 10 electron volts. The ability of an electromagnetic wave, photons, to ionize an atom or molecule thus depends on its frequency, which determines the energy of a photon of the radiation. An energy of 10 eV is about 1.6 × 10^18 joules, which is a typical binding energy of an outer electron to an atom, or organic molecule. This corresponds with a frequency of 2.4115 Hz, and a wavelength of 125 nm, this is infrared ultraviolet, or less. Ultraviolet radiation, mostly non-ionizing, but with many similar properties to ionizing radiation. Ultraviolet of ionizing wavelengths from 10 nm to 125 nm ionizes air molecules, and this interaction causes it to be strongly absorbed by air. Ionizing UV therefore does not penetrate Earth's atmosphere to a significant degree, and is therefore sometimes referred to as vacuum ultraviolet. Although present in space, this part of the UV spectrum is not of biological importance, because it does not reach living organisms on Earth. Some of the ultraviolet spectrum that does reach the ground, the part that begins above energies of 3.1 eV, or wavelength less than 400 nm, is non-ionizing, but is still biologically hazardous due to the ability of single photons of this energy to cause electronic excitation in biological molecules, and thus damage them by means of unwanted reactions. An example is the formation of pyrimidine dimers in DNA, which begins at wavelengths below 365 nm, 3.4 eV, which is well below ionization energy. This property gives the ultraviolet spectrum some of the dangers of ionizing radiation in biological systems without actual ionization occurring. In contrast, visible light and longer wavelength electromagnetic radiation, such as infrared, microwaves, and radio waves, consists of photons with too little energy to cause damaging molecular excitation, and thus this radiation is far less hazardous per unit of energy. X-ray. X-ray X-rays are electromagnetic waves with a wavelength less than about 10 to 9 m, greater than 3 by 1017 Hz, and 1240 f. A smaller wavelength corresponds to a higher energy according to the equation E equals hc/. E is energy, h is Planck's constant, c is the speed of light, is wavelength. A packet of electromagnetic waves is called a photon. When an X-ray photon collides with an atom, the atom may absorb the energy of the photon and boost an electron to a higher orbital level, or if the photon is very energetic, it may knock an electron from the atom altogether, causing the atom to ionize. Generally, larger atoms are more likely to absorb an X-ray photon, since they have greater energy differences between orbital electrons. Soft tissue in the human body is composed of smaller atoms than the calcium atoms that make up bone, hence there is a contrast in the absorption of X-rays. X-ray machines are specifically designed to take advantage of the absorption difference between bone and soft tissue, allowing physicians to examine structure in the human body. Gamma radiation. Gamma radiation consists of photons with a wavelength less than 3 by 10⁻11 meters, greater than 1019 Hz, and 41.4 keV. Gamma radiation emission is a nuclear process that occurs to rid the decaying nucleus of excess energy after it has emitted either alpha or beta radiation. Both alpha and beta particles have an electric charge and mass, and thus are quite likely to interact with other atoms in their path. Gamma radiation, however, is composed of photons which have neither mass nor electric charge, and, as a result, penetrates much further through matter than either alpha or beta radiation. Gamma rays can be stopped by a sufficiently thick layer of material, where the stopping power of the material per given area depends mostly, but not entirely, on the total mass along the path of the radiation, regardless of whether the material is of high or low density. However, as is the case with X-rays, materials with high atomic number such as lead or depleted uranium add a modest, typically 20% to 30%, amount of stopping power over an equal mass of less dense and lower atomic weight materials, such as water or concrete. Alpha radiation. Alpha particles are helium-4 nuclei, 2 protons and 2 neutrons. They interact with matter strongly due to their charges, and at their usual velocities only penetrate a few centimeters of air, or a few millimeters of low-density material, such as the thin micromaterial which is specially placed in some Geiger counter tubes to allow alpha particles in. This means that alpha particles from ordinary alpha decay do not penetrate skin, and cause no damage to tissues below. Some very high-energy alpha particles compose about 10% of cosmic rays, and these are capable of penetrating the body, and even thin metal plates. However, they are of danger only to astronauts, since they are deflected by the Earth's magnetic field and then stopped by its atmosphere. Alpha radiation is dangerous when alpha-emitting radioisotopes are ingested, breathed or swallowed. This brings the radioisotope close enough to sensitive tissue for the alpha radiation to damage cells. Per unit of energy, alpha particles are at least 20 times more effective at cell damage as gamma rays and X-rays. See relative biological effectiveness for a discussion of this. Examples of highly poisonous alpha emitters are radium, radon, and polonium. Beta radiation. Beta- radiation consists of an energetic electron. It is more ionizing than alpha radiation, but less than gamma. Beta radiation from radioactive decay can be stopped with a few centimeters of plastic, or a few millimeters of metal. It occurs when a neutron decays into a proton in a nucleus, releasing the beta particle and an antineutrino. Beta radiation from Planck accelerators is far more energetic and penetrating than natural beta radiation. It is sometimes used therapeutically in radiotherapy to treat superficial tumors. Beta plus radiation is the emission of positrons, which are the antimatter form of electrons. When a positron slows down to speeds similar to those of electrons in the material, the positron will annihilate an electron, releasing 2 gamma photons of 511 keV in the process. those two gamma photons will be traveling in approximately opposite direction. The gamma radiation from positron annihilation consists of high-energy photons and is ionizing. Neutron radiation. Neutrons are categorized according to their speed. Neutron radiation consists of free neutrons. These neutrons may be emitted during either spontaneous or induced nuclear fission. Neutrons are the only type of ionizing radiation that can make other objects or material radioactive. This process, called neutron activation, is the primary method used to produce radioactive sources for use in medical, academic, and industrial applications. Even comparatively low-speed thermal neutrons will cause neutron activation. In fact, they cause it more efficiently. Neutrons do not ionize atoms in the same way that charged particles such as protons and electrons do, by the excitation of an electron, because neutrons have no charge. It is through their absorption by and the creation of unstable nuclei that they cause ionization. Such neutrons are indirectly ionizing. Even neutrons without significant kinetic energy are indirectly ionizing, and are thus a significant radiation hazard. In addition, high-energy, high-speed neutrons have the ability to directly ionize atoms. One mechanism by which high-energy neutrons ionize atoms is to strike the nucleus of an atom and knock the atom out of a molecule, leaving one or more electrons behind as the chemical bond is broken. This leads to production of chemical free radicals. In addition, very high-energy neutrons can cause ionizing radiation by neutron spallation, or knockout, wherein neutrons cause emission of high-energy protons from atomic nuclei, especially hydrogen nuclei, on impact. The last process imparts most of the neutron's energy to the proton, much like one billiard ball striking another. The charged protons and other products from such reactions are directly ionizing. High-energy neutrons are very penetrating and can travel great distances in air, hundreds or even thousands of meters, and moderate distances, several meters, in common solids. They typically require hydrogen-rich shielding, such as concrete or water, to block them within distances of less than a meter. A common source of neutron radiation occurs inside a nuclear reactor, where a meters-thick water layer is used as effective shielding. Non-ionizing radiation. The kinetic energy of particles of non-ionizing radiation is too small to produce charged ions when passing through matter. For non-ionizing electromagnetic radiation, C-types, below, the associated particles, photons, have only sufficient energy to change the rotational, vibrational or electronic valence configurations of molecules and atoms. The effect of non-ionizing forms of radiation on living tissue has only recently been studied. Nevertheless, different biological effects are observed for different types of non-ionizing radiation. Even non-ionizing radiation is capable of causing thermal ionization if it deposits enough heat to raise temperatures to ionization energies. These reactions occur at far higher energies than with ionization radiation, which requires only single particles to cause ionization. A familiar example of thermal ionization is the flame ionization of a common fire, and the browning reactions in common food items induced by infrared radiation during broiling-type cooking. Non-ionizing electromagnetic radiation. The electromagnetic spectrum. The electromagnetic spectrum is the range of all possible electromagnetic radiation frequencies. The electromagnetic spectrum, usually just spectrum, of an object is the characteristic distribution of electromagnetic radiation emitted by, or absorbed by, that particular object. The non-ionizing portion of electromagnetic radiation consists of electromagnetic waves that, as individual quanta, or particles, see photon, are not energetic enough to detach electrons from atoms or molecules, and hence cause their ionization. These include radio waves, microwaves, infrared, and, sometimes, visible light. The lower frequencies of ultraviolet light may cause chemical changes and molecular damage similar to ionization, but is technically not ionizing. the highest frequencies of ultraviolet light, as well as all X-rays and gamma rays, are ionizing. The occurrence of ionization depends on the energy of the individual particles or waves, and not on their number. An intense flood of particles or waves will not cause ionization if these particles or waves do not carry enough energy to be ionizing. Unless they raise the temperature of a body to a point high enough to ionize small fractions of atoms or molecules by the process of thermal ionization, this, however, requires relatively extreme radiation intensities. Ultraviolet light. As noted above, the lower part of the spectrum of ultraviolet, from 3F to about 10F, is non-ionizing. However, the effects of non-ionizing ultraviolet on chemistry, and the damage to biological systems exposed to it, including oxidation, mutation, and cancer, are such that even this part of ultraviolet is often compared with ionizing radiation. Visible light. Light, or visible light, is a very narrow range of electromagnetic radiation of a wavelength that is visible to the human eye, or 380-750 nm, which equates to a frequency range of 790 to 400 Thz respectively. More broadly, physicists refer to light as electromagnetic radiation of all wavelengths, whether visible or not. Infrared. Infrared, IR. Light is electromagnetic radiation with a wavelength between 0.7 and 300 micrometers, which corresponds to a frequency range between 430 to 1 Thz respectively. IR wavelengths are longer than that of visible light, but shorter than that of microwaves. Infrared may be detected at a distance from the radiating objects by feel. Infrared sensing snakes can detect and focus infrared by use of a pinhole lens in their heads. Bright sunlight provides an irradiance of just over 1 kilowatt per square meter at sea level. Of this energy, 53% is infrared radiation, 44% is visible light, and 3% is ultraviolet radiation. Microwave. Microwaves are electromagnetic waves with wavelengths ranging from as short as 1 mm to as long as 1 meter, which equates to a frequency range of 300 GHz to 300 MHz. This broad definition includes both UHF and EHF millimeter waves, but various sources use different other limits. In all cases, microwaves include the entire super-high frequency band, 3 to 30 GHz. Or 10 to 1 centimeter at minimum, with RF engineering often putting the lower boundary at 1 GHz, 30 centimeters, and the upper around 100 GHz, 3 mm. Radio waves. Radio waves are a type of electromagnetic radiation with wavelengths in the electromagnetic spectrum longer than infrared light. Like all other electromagnetic waves, they travel at the speed of light. Naturally occurring radio waves are made by lightning or by certain astronomical objects. Artificially generated radio waves are used for fixed and mobile radio communication, broadcasting, radar, and other navigation systems, satellite communication, computer networks, and innumerable other applications. Different frequencies of radio waves have different propagation characteristics. In the Earth's atmosphere, long waves may bend at the rate of the curvature of the Earth and may cover a part of the Earth very consistently. Shorter waves travel around the world by multiple reflections off the ionosphere and the Earth. Much shorter wavelengths bend or reflect very little and travel along the line of sight. Very low frequency, VLF. Very low frequency, or VLF, refers to a frequency range of 30 Hz to 3 kHz, which corresponds to wavelengths of 100,000 to 10,000 meters respectively. Since there is not much bandwidth in this range of the radio spectrum, only the very simplest signals can be transmitted, such as for radio navigation. Also known as the myriameter band or myriameter wave, as the wavelengths range from 10 to 1 myriameter, an obsolete metric unit equal to 10 kilometers. Extremely low frequency, ELF. Extremely low frequency, ELF, is radiation frequencies from 3 to 30 Hz, 108 to 107 meters respectively. In atmosphere science, an alternative definition is usually given, from 3 Hz to 3 kHz. In the related magnetosphere science, the lower frequency electromagnetic oscillations, pulsations occurring below 3 Hz, are considered to lie in the ULF range, which is thus also defined differently from the ITU radio bands. Thermal radiation, heat. Thermal radiation is a common synonym for infrared radiation emitted by objects at temperatures often encountered on Earth. Thermal radiation refers not only to the radiation itself, but also the process by which the surface of an object radiates its thermal energy, in the form blackbody radiation. Infrared or red radiation from a common household radiator or electric heater is an example of thermal radiation, as is the heat emitted by an operating incandescent light bulb. Thermal radiation is generated when energy from the movement of charged particles within atoms is converted to electromagnetic radiation. As noted above, even low-frequency thermal radiation may cause temperature ionization, whenever it deposits sufficient thermal energy to raise its temperatures to a high enough level. Common examples of this are the ionization, plasma, seen in common flames, and the molecular changes caused by the browning during food cooking, which is a chemical process that begins with a large component of ionization. Blackbody radiation. Blackbody radiation is an idealized spectrum of radiation emitted by a body that is at a uniform temperature. The shape of the spectrum and the total amount of energy emitted by the body is a function of the absolute temperature of the body. The radiation emitted covers the entire electromagnetic spectrum, and the intensity of the radiation, power/unit area, at a given frequency is described by Planck's law of radiation. For a given temperature of a black body there is some frequency at which the maximum amount of radiation is emitted. That maximum radiation frequency moves toward higher frequencies as the temperature of the body increases. The frequency at which the black body radiation is at maximum is given by Wien's displacement law, and is a function of the body's absolute temperature. A black body is one that emits at any temperature the maximum possible amount of radiation at any given wavelength. A black body will also absorb the maximum possible incident radiation at any given wavelength. A black body with a temperature at or below room temperature would thus appear absolutely black, as it would not reflect any incident light, nor would it emit enough radiation at visible wavelengths for our eyes to detect. Theoretically, a black body emits electromagnetic radiation over the entire spectrum, from very low-frequency radio waves to X-rays, creating a continuum of radiation. Discovery. Electromagnetic radiation of wavelengths other than light were discovered in the early 19th century. The discovery of infrared radiation is ascribed to William Herschel, the astronomer. Herschel published his results in 1800, before the Royal Society of London. Herschel, like Ritter, used a prism to refract light from the sun, and detected the infrared, beyond the red part of the spectrum, through an increase in the temperature recorded by a thermometer. In 1801, the German physicist Johann Wilhelm Ritter made the discovery of ultraviolet by noting that the rays from a prism darken silver chloride preparations more quickly than violet light. Ritter's experiments were an early precursor to what would become photography. Ritter noted that the UV rays were capable of causing chemical reactions. The first radio waves detected were not from a natural source, but were produced deliberately and artificially by the German scientist Heinrich Hertz in 1887, using electrical circuits calculated to produce oscillations in the radio frequency range, following formulas suggested by the equations of James Clerk Maxwell. Wilhelm Röntgen discovered and named X-rays. While experimenting with high voltages applied to an evacuated tube on the 8th of November, 1895, he noticed a fluorescence on a nearby plate of coated glass. Within a month, he discovered the main properties of X-rays that we understand to this day. In 1896, Henry Becquerel found that rays emanating from certain minerals penetrated black paper and caused fogging of an unexposed photographic plate. His doctoral student Marie Curie discovered that only certain chemical elements gave off these rays of energy. She named this behavior radioactivity. Alpha rays, alpha particles, and beta rays, beta particles, were differentiated by Ernest Rutherford through simple experimentation in 1899. Rutherford used a generic pitch-blende radioactive source and determined that the rays produced by the source had differing penetrations in materials. One type had short penetration, it was stopped by paper, and a positive charge, which Rutherford named alpha rays. The other was more penetrating, able to expose film through paper, but not metal, and had a negative charge, and this type Rutherford named beta. This was the radiation that had been first detected by Becquerel from uranium salts. In 1900, the French scientist Paul Villard discovered a third neutrally charged, and especially penetrating type of radiation from radium, and after he described it, Rutherford realized it must be yet a third type of radiation, which in 1903 Rutherford named gamma rays. Henri Becquerel himself proved that beta rays are fast electrons, while Rutherford and Thomas Royds proved in 1909 that alpha particles are ionized helium. Rutherford and Edward Andrade proved in 1914 that gamma rays are like X-rays, but with shorter wavelengths. Cosmic ray radiation striking the Earth from outer space were finally definitively recognized and proven to exist in 1912 as the scientist Victor Hess carried an electrometer to various altitudes in a free balloon flight. The nature of these radiations was only gradually understood in later years. Neutron radiation was discovered with the neutron by Chadwick in 1932. A number of other high-energy particulate radiation such as positrons, muons, and pions were discovered by cloud chamber examination of cosmic ray reactions shortly thereafter, and other types of particle radiation were produced artificially in particle accelerators through the last half of the 20th century. Uses of radiation in medicine. Radiation and radioactive substances are used for diagnosis, treatment, and research. X-rays, for example, pass through muscles and other soft tissue, but are stopped by dense materials. This property of X-rays enables doctors to find broken bones and to locate cancers that might be growing in the body. Doctors also find certain diseases by injecting a radioactive substance and monitoring the radiation given off as the substance moves through the body. Radiation used for cancer treatment is called ionizing radiation because it forms ions in the cells of the tissues it passes through as it dislodges electrons from atoms. This can kill cells or change genes so the cells cannot grow. Other forms of radiation such as radio waves, microwaves, and light waves are called non-ionizing. They don't have as much energy and are not able to ionize cells. In communication. All modern communication systems use forms of electromagnetic radiation. Variations in the intensity of the radiation represent changes in the sound, pictures, or other information being transmitted. For example, a human voice can be sent as a radio wave or microwave by making the wave vary to correspond variations in the voice. In science, researchers use radioactive atoms to determine the age of materials that were once part of a living organism. The age of such materials can be estimated by measuring the amount of radioactive carbon they contain in a process called radiocarbon dating. Similarly, using other radioactive elements, the age of rocks, and other geological features, even some man-made objects, can be determined. This is called radiometric dating. Environmental scientists use radioactive atoms, known as tracer atoms, to identify the pathways taken by pollutants through the environment. Radiation is used to determine the composition of materials in a process called neutron activation analysis. In this process, scientists bombard a sample of a substance with particles called neutrons. Some of the atoms in the sample absorb neutrons and become radioactive. The scientists can identify the elements in the sample by studying the emitted radiation.